Chapter 13 is on solutions. Chapter 13, Section 1 begins with mixtures and distinguishing between a suspension, a colloid, and a solution. For a suspension, that's going to be a mixture that appears uniform in composition, but if you let it sit out for a while, it will eventually separate out into its component parts. So for instance, muddy water may look like it's just one uniform substance, and then if you let it sit on a counter for a while in a container, it will separate out into, some dirt particles, probably some little pebbles, some water, all the different pieces that would make that up. A colloid is when you have small particles that are suspended in a solvent that do not settle out. So for example, milk is made of a combination of fat and whey, different emulsions or foams or gels. These are all going to be colloids. So they're kind of an intermediate between the heterogeneous suspension and then the homogeneous mixture of a solution. So a solution then is made up of a solvent and a solute. The solvent is the substance in which the solute is dissolving into, and then the solute is what is trying to be dissolved. We call it an aqueous solution if the solvent is water. Concentration is going to be the amount of solute that is in a specific amount or solvent or solution. So you can have a very concentrated solution of a chemical, which would we would just call that concentrated, and we could also have a dilute solution, which means that it has a low concentration. We will mix up some different concentrations of some substances, sodium hydroxide being one of them. Using these flasks here in the lab, we'll actually do some calculations and you'll figure out how much of the solid that you'll need to add. You add that to this volumetric flask with some water. You fill it up to the line, put a stopper on it, and then you can mix them up and get whatever concentration that you need to complete the lab. To measure concentration, there's a variety of different units you can use. The main one used is molarity, which is represented by a capital M, and that's going to be the moles of solute divided by the liters of solution. Something that is, say, 1 molar is going to be relatively dilute, whereas something that's like 6 molar is a pretty concentrated solution. 12 molar would be something that's very, very concentrated. Molality is another way to measure concentration, and it's represented by a lowercase italicized m, and that's going to be moles of solute as well, but this time we're dividing by kilograms of solvent. Another one you might have heard of is parts per million. That's milliliters of solute divided by 1 million milliliters of solution. And that's one that the EPA uses a lot in regulating like drinking water conditions, things like that. So that's ppm, or parts per million. Here's an example of a molarity problem. So it says, what's the molarity of a potassium chloride solution that has a volume of 400 milliliters and contains 85 grams of KCl? So what we know is the volume and the mass of our KCl. For our molarity equation, which is molarity is equal to moles over liters, we would then need to convert our milliliters into liters, which we do by dividing by 1,000. That'll give us 0.4 liters. And then we are given grams, which we would have to convert to moles. So we're going to use potassium chloride's molar mass, which is 74.6, and find out how many moles of the KCl we have. Then we're able to divide our moles by our liters, and that would tell us that this solution is 2.85 molar, and we just have to write that capital M to show that we're talking about molarity. This is a molality practice problem. This one says how many moles of sodium fluoride are required to make a 0.3 molal solution using a 0.6 kilograms of water. So we have the molality this time, and we have the kilograms of our solvent. We want to find out how many moles we need. So we're going to write in our equation, molality is equal to moles over kilograms, and then we're solving for moles, so we want to multiply molality by kilograms. So 0.3 molal by 0.6 kilograms is going to give us 0.18 moles. If we were to then want grams of how much sodium fluoride we had, so for instance we could maybe weigh it out in the lab and actually mix up this solution, then we would go ahead and use the molar mass at the end to cancel out our mole units and convert it into grams. You can also separate out mixtures. We've talked about a couple of these ways before and done a few of these methods in the lab. One is through filtration, and that's similar to a setup that we've used a number of times in the lab, where you have your filter paper in your funnel and you pour your solution through your funnel, and the solids will get stuck in the filter paper and the liquids will go through. That's one way to separate out a mixture. Evaporation could be another. You know, it's used a lot in the cooking process, and then also in kind of a purification process. You can evaporate off one of the liquids and be left with the remaining part of the mixture. There's a centrifuge, which is like this piece of equipment here. You'll probably use if you take a lab in college. With the centrifuge, you put your mixture in test tubes, put them in the centrifuge, and then turn it on, and it spins them around real fast. And that will separate them into their component layers, which you could then pipette out when you're finished. Distillation, this is used a lot in organic chemistry labs. This is mainly used for purification. We use it a lot to get drinking water from seawater, and that's kind of working with evaporation and using different boiling points to try to separate out and purify these mixtures. And then the last one is chromatography, which you might have done in biology class before. With chromatography, what you're going to be doing is separating out these components based on their component parts or their capillary action, which is their attraction to the surface of a solid. So like we will test in lab M&M dyes versus Reese-Peasy dyes to see what their component colors are, see if they actually use the same dyes. And it looks similar to this structure here. You're going to make a chromatogram, which is this piece of paper. You'll put your different samples that you want to test on there, so your samples of your different mixtures, and then you're going to put it in a solvent. And as this liquid solvent travels up the paper, it's going to separate out the mixture into its component parts, and you'll be able to see which colors actually go into those particular dyes.